This unit is on differential equations. Quite simply, differential equations are any equations that contain a derivative. So that can be y prime, y double prime, y triple prime. So it's not necessarily the first derivative that it contains. It might contain the second derivative or the third derivative or any derivative. And it also can contain more than one derivative. And you'll see I abbreviated differential equation DE, and that'll be a common abbreviation throughout this unit. Sometimes in college they call it DVQ, but that's even longer than DE, so I'm just going to call it DE for differential equation. There are 4 steps to solving a differential equation, and they are listed right here. The first is that you have to convert to Leibniz notation. Newton used the notation with primes, f prime, y prime, all that stuff. Leibniz used the notation dy over dx, or sometimes we'll be using dy over dt. So all that means, and you'll see this very clearly in the examples, is that anytime we have a y prime, we change it to dy over dx, or if it's appropriate, dy over dt. So that's all that first step means. Second step, separate the variables. We're going to have 2 variables, either x's and y's or t's and y's, and we need to get all the y's on one side of the equation and all the x's or t's on the other side of the equation. The third step is to integrate both sides, or take the integral of both sides. So we'll be taking the antiderivative and the integral of both sides. Then the fourth step is to simplify. Y has to end up by itself. Sometimes when you take the antiderivative, you'll end up with y squared or 2y or natural log of y, and you have to get the y just all the way by itself. So here's our first example, and you'll notice the first few examples are going to be very simple. They're going to seem very similar to things we've done before, but we're just building up to the newer things. So first example, y prime equals 11x plus 5. So the first step, I usually just use the words Leibniz, separate, integrate, simplify. Leibniz, separate, integrate, simplify. So the first step is to change into Leibniz notation. So we change y prime to dy over dx. So that's step 1. You just change y prime to dy over dx. The second step is to separate. If you notice right now, there's a dy and a dx together, and we want the y's and the x's to be separated. So we multiply both sides by dx, and we get this. So we've done the first 2 steps, Leibniz, separate. The next step is to integrate. So we take the integral of both sides. Okay, now the integral of dy just turns into y. Just so you know, technically what's changing into the y is the understood 1 in front of the dy. If you think about it, the antiderivative of 1 is y or x or whatever your variable is. So this side gives us y. On this side, the antiderivative will be 11 halves x squared plus 5x plus c. And we don't have to worry about simplifying because y is already by itself. So that's an example of solving a differential equation. Okay, moving on, we have y prime equals x squared sine of x cubed. Y prime needs to be rewritten in Leibniz notation. First step is Leibniz. The next step is to separate. Again, all we have to do is multiply the dx over. There will be more to that step in some later problems, but so far that's all we have to do. The next step is to integrate. So we take the integral of both sides. Integral of dy is just y. Over here we need to use u substitution. U is going to be x cubed. I choose that because it's inside of the trig function. The derivative of that will be 3x squared dx. Now we have an x squared into dx, but no 3, so we need to divide that over. We get 1/3 du equals x squared dx. So we'll have 1/3 integral of sine u du. Now the antiderivative of sine is negative cosine, so we get negative 1/3 cosine of u, which is x cubed, plus c. And again, y just turned out to be by itself already, so there was no simplifying needed. Okay, now we're starting to get into things that are really different from what we've done before. The first 2 really weren't any different than integrals and antiderivatives we've done previously, but now, with this example, you'll see that there are some differences that can appear when we're doing differential equations. First step, Leibniz. change y prime to dy over dx. Second step, separate. Multiply the dx over and multiply the y over. Leibniz, separate. Now we integrate. Antiderivative of y is 1/2 y squared. Antiderivative of 2x is x squared plus c. So here we do need to do some simplifying. First of all, we have to get rid of the 1/2, so we multiply both sides by 2. Okay, just to let you know, you notice I did not put a 2 in front of the c. It's not mathematically incorrect if you do. You could write this, and again, it would not mathematically be incorrect. But just mathematicians never do. They never do write a 2 in front of the c. And the reason is 2c is still just a constant. So instead of just making the formula more complicated, we just know that, okay, 2 times a constant is still just a constant, so we're just going to leave it as plus c. So the point is you're still adding a constant. Okay, and then the last step is to take the square root. So we take the square root of both sides. When you do so, don't forget that you'll have plus or minus in front. Now just so you know, there will be times in our book in particular, and even on the AP test, where they may stop right here at this problem, but most of the time they're going to require you to go this far. So I would recommend you always get y down to the bare minimum. But just so you don't get confused in case it happens, occasionally they will stop with the exponent. Basically, y can have an exponent sometimes, but it can never have coefficients. I've never seen them leave it with a square root or a natural log or an e. But occasionally if it's y squared or y cubed, they will leave it that way. Alright, so next up, we have dy over dx equals 6x minus 1 over 2y, excuse me. If you notice, this one's already in Leibniz notation, and sometimes that'll happen. Sometimes it'll already be in Leibniz notation for you, and you don't have to change it. So we just need to separate. Well, basically that means cross-multiplying in this case, because you multiply both sides by dx and 2y. That won't always be the case, but that's how it worked out on this particular problem. So that's separated for us. Now we integrate. Antiderivative of 2y is y squared. Antiderivative of 6x is 3x squared minus x. Sorry, I don't need those parentheses. Let me erase those. 3x squared minus x plus c will be the antiderivative on the right side. Okay, so again, you may see them leave the answer like that, but more often they will go ahead and take the square root of both sides, and you'll get plus or minus the square root of 3x squared minus x plus c. And that plus c does need to be inside the square root. I believe there are just two more examples. First up, y prime equals 3x squared y. We have dy over dx because we want to change it to Leibniz notation. That's step 1. Step 2 is to separate, so I'm going to multiply the dx over and then divide the y. Okay, now we do the integral of both sides. That dy over y should be a familiar form. It's the same thing as du over u, or derivative over the original. So that's simply the natural log. Natural log, the absolute value of y. Antiderivative of 3x squared is x cubed plus c. So both sides need to be raised as powers of e. E raised to the natural log of y just gives you y. And if you remember, we talked about how this c comes down front, and we'll write it as ce to the x cubed. Okay, in case you didn't see that in class or you haven't done something like that before, I want to briefly show you why that c comes down front. This is our answer, by the way. This other part's just kind of an aside to explain why the c came down front. So we had e to the x cubed plus c. Well, that could be rewritten as e to the x cubed times e to the c. Now, if you're not sure about that, think about going this direction. It's pretty common for us when we're multiplying two things to go that direction, and we simply add the exponents when we do that. Think about it, x squared times x cubed is x to the 5th, because we add the 2 and the 3. Okay, so same idea here. but there's no reason you can't go in the reverse order. You can rewrite x cubed, or x to the fifth, as x cubed times x squared. So the bottom line here is that you can separate these two things this way, and then e is just a number and c is just a number. So e raised to the c, a number raised to a number, is just a number. So we just call that capital C, just to make it different from the other one, and then I just brought it out front. If that doesn't all make sense to you, what you just got to remember is that if there's a constant, if you have a plus c that ends up in the exponent of e, it's going to come down front every time. So if you have a plus c that's up in the exponent of e, you bring it down front every time. Okay, last example. This one's already in Leibniz notation, so you don't have to worry about that, but there is a lot of separating to do. So first, I'm going to multiply both sides by dx. Now, there's not necessarily a right or wrong way of what to do next, but you've got to separate. I'm going to divide both sides by x squared plus 4. And then last step is to divide both sides by y, because I've got to get this moved over. So dy over y equals 2x over x squared plus 4 dx. Now I need to take the integral of both sides. Okay, well, if you notice over here on the right hand side, if we use u substitution, u is x squared plus 4 and du would be 2x dx, which is a perfect match, and you just end up with du over u. So both sides are actually going to be the natural log. This side's natural log of y, this side's the natural log of x squared plus 4 plus c. To get rid of those natural logs, we have to make both sides powers of e. So on the left side, it's very simple. It just turns out to be y. On the right side, before the e and the natural log can cancel out, you have to take this c and bring it down front. So I'm going to go ahead and write that capital C. So that's already down front for us. Now e to the natural log cancels out, and we're left with x squared plus 4. And that would be our final answer. Alright, to find out the homework, make sure you check the website. But if you want an idea of where you can get some practice problems, if you just look in this area, not necessarily just the evens and odds, but this was the homework I assigned this particular time. And anything in those sections, evens or odds, would be good practice for this.